Example 6, similar to example 4 and example 5, deals with empirical formulas and gravimetric analysis. But this time we're looking at a covalent molecular compound rather than an ionic compound. And for ionic compounds, the chemical formula is an empirical formula. But for covalent molecular compounds, the empirical formula is not the same as the molecular formula, and sometimes it's vital to know the molecular formula. So why do we need to know the molecular formula? Because for covalent molecular compounds, the actual properties really depend on the number of atoms in that molecule. And so as an example here, it says, for example, glucose and acetic acid both have the same empirical formula, which is CH2O, but they've got very different molecular formula. Acetic acid, which is the stuff in vinegar, is CH3COOH, so it's got 2 carbons, 4 hydrogens and 2 oxygens, hence the ratio CH2O. And glucose, which is sugar, has molecular formula C6H12O6, which once again is a ratio of 1 to 2 to 1. So they've both got the same empirical formula, but they've got very different properties and very different molecular formula. Thus, for these covalent molecular compounds, it's very important to know not just their empirical formula, but it's very important to know their actual molecular formula as well. And that's what example 6 is all about. So in example 6, we've got 2.2 grams of organic acid, which is a little code word for as you do more chemistry, you know that's a covalent molecular substance, was decomposed. They broke this organic acid down, they broke this covalent molecular compound down, and they found its composition. They found it in the decomposition products. There was exactly 1.2 grams of carbon and 0.2 grams of hydrogen, and the rest was oxygen. And so you've got to do two things. First of all, you've got to calculate the empirical formula of the compound, which we'll solve in blue. And then it says the molecular weight or molar mass was determined by chromatography, which is a separation technique, to be 88.1. That should be grams per mole. If we know that, calculate the molecular formula. Well, let's do the first thing first. Let's calculate the empirical formula first, and then we can worry about the actual molecular formula. So how do we figure out the empirical formula? Well, this links back to what we did in examples 4 and 5. The empirical formula is equal to the mole ratio, and to know that we've got to calculate the moles of each element in that compound. Because number of moles equals mass of a molar mass, we can calculate the number of moles if we know the molar mass, which we take from the periodic table, and the mass of each element in the compound. So to find the moles of each element, we need to know the mass and the molar mass of those elements. So we've been told the mass of carbon is 1.2 grams. We've been told the mass of hydrogen is 0.2 grams. We haven't been told the mass of oxygen, though. We've got to calculate that. So what's the mass of oxygen? See if you can think about how you can find the mass of oxygen here. Have a little pause it if you wish, have a think. Well, the mass of oxygen is just going to be the mass of the compound. Take away the mass of carbon, take away the mass of hydrogen, because this compound, they told us, only had carbon, hydrogen, and oxygen, and therefore the mass of oxygen is just going to be that difference. So the mass of oxygen is 2.2, take away 1.2, take away 0.2, we've got 0.8 grams of oxygen in this compound. Now we know the masses of all three things, we can start figuring out the moles of all three things. So, remember, the oxygen and hydrogen in this compound are no longer diatomic molecules, they're just individual atoms we consider on the atomic basis. So for each of them, we're trying to find the moles. We now know the mass of each one, and from the periodic table we know the molar mass of each one. So you should be able to go ahead now and calculate how many moles of each of these particular elements are in this compound. I'd like you to pause and have a go at this before you check your answers, so see if you can figure out the number of moles of each of these elements in this particular compound. Okay, so we've done this calculation now, so let's see. First of all, we substitute number of moles equals mass of a molar mass, and therefore for carbon it's 1.2 divided by 12.01, for hydrogen it's 0.2 divided by 1.008, and for oxygen it's 0.8 divided by 16. We do those sums and we get 3 different values for molar mass, and all 3 I'm going to put in my calculator as A, B and C, rather than trying to write down those whole big numbers. So we know the moles of each one. Now we need to find the empirical formula, which is just like we did before. We need to find the ratio of moles, the number of moles of carbon to hydrogen to oxygen. And in this case, it's going to be 0.9991 to 0.1984 to 0.05, or to ABC in your calculator. And just like before, to find that as a simple whole number ratio, we've got to divide by the smallest number, which in this case is 0.05, the oxygen ratio. So dividing all those by 0.05 gives us the ratio 1.998 to 3.968 to 1, which isn't a whole number ratio, but this was done in an experiment, and we know experiments have errors. So when you see these things, you know there's going to be a tiny amount of error in the results, and this is so close to 2, and that's so close to 4, that we can round this off to a nice simple whole number ratio. We can assume that means that the empirical formula is 2 to 4 to 1, and therefore the empirical formula must be C2H4O. There's 2 carbons for every 4 hydrogens for every 1 oxygen. We've just figured out the empirical formula of this compound. But like we said before, knowing the empirical formula of a covalent molecular substance is okay, but it's actually much more useful to know the molecular formula. So how are we going to figure out the molecular formula? Well, let's have a look over here in the purple. The empirical formula tells us the ratio of atoms, but knowing the molar mass of the molecule, so knowing there's molar mass here, which they've given us, we can actually use that to calculate exactly how many atoms are in the molecule, and thus calculate the molecular formula, which is what we're trying to do. we don't know how many oxygens there are in the molecule. So we can't pretend right now we know the exact molecular formula, but we can have a little guess. We can use algebra to figure this out. So we don't know how many oxygens there are in this molecule, but we can say that there's X. Let's just say there's X oxygen atoms in every molecule. And according to the empirical formula, if we've got X oxygen atoms in the molecule, knowing the ratio is 2 to 4 to 1, we can say there must be 4X hydrogens and 2X carbons in the molecule. And therefore, we know the molar mass. The molar mass is the sum of all the atomic weights of all the elements in the compound's formula. Thus, algebraically, the molar mass must be 2x carbons, which is 2x times 12.01. We said there's 4x hydrogens, so the mass of that is 4x times 1.08. And we said there's x oxygen, so the mass of that must be x times 16. So going right back to how we calculated molar mass previously, we can use this algebra to actually figure out the algebraic formula for the molar mass. Now, we can combine that with this data. We actually know the molar mass of this compound because of the question. So now we can say that 88.1, which is what they told us, 88.01 there, sorry, 88.1 equals 2x times 12.01 plus 4x times 1.08 plus x times 16. Now we can just do our skills in maths. We can solve this for x to find out what x must be. We solve this, and it turns out that x is equal to 2. And that tells us there's not x oxygens in a molecule, there's 2 oxygens in the molecule. But because we already know the empirical formula, that means we can find the molecular formula. If there's 2 oxygens, by that ratio there must be 8 hydrogens and there must be 4 carbons. So the empirical formula was C2H4O, but the actual molecular formula was C4H8O2. So by using this molar mass and using some algebra, we could figure out the actual molecular formula of that covalent molecular substance.